K2 Airways Flight KTA 1732, a Boeing 737-400 freighter aircraft, crashed in the Arabian Sea on 7 July 2026. All 5 crew members are presumed dead. ADS-B data indicate that the flight departed Sharjah Airport, SHJ, in the United Arab Emirates at 15:02 UTC on a flight to Karachi, KHI. At 16:17 UTC, while following Airway G216, the aircraft began a shallow right turn at approximately flight level 350. The maneuver subsequently developed into a much tighter turn, a descent of about 5,350 feet, a rapid climb of about 7,175 feet, and finally a steep terminal descent. According to a statement by the Pakistan Airports Authority, the flight reported a navigational system issue at 16:18 UTC and requested heading assistance and was promptly guided by Karachi Area Control Center. At 16:21 UTC, the aircraft was observed on radar rapidly descending with a rapid heading change. Subsequently, radar contact and communication were lost. On 8 July, floating wreckage from the aircraft was located. The airplane was destroyed. Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. This episode is Flight KTA 1732. What the evidence actually shows. Speculation is rife in the media with multiple reports of what happened. The aircraft experienced radio and satellite jamming by Iran. The aircraft was shot down by an Iranian missile. The aircraft had a long history of faults. The inertial reference unit failed and the aircraft was grounded in Sharjah. A replacement inertial reference unit was flown in from the USA. The aircraft was repaired incorrectly in Sharjah. The aircraft was subject to turbulence and structural failure. There was a cargo fire and catastrophic mid-air breakup. And one comment, it was only a cargo flight, so no need to recover the FDR or CVR. There have even been fake cockpit voice recordings and communications with the ATC. The available evidence establishes that KTA 1732 experienced serious navigation or tracking anomalies during the initial climb, and subsequently completed a long and apparently stable cruise, and then suffered a catastrophic loss of control. It does not establish Iranian jamming, hostile interference, or a missile attack. The notion that cargo flights are not so important misses the point. Safety lessons should be learned from all accidents, including cargo flights, in order to prevent future similar accidents. For example, for this reason, the NTSB undertook a rigorous investigation into the UPS Flight 2976, which crashed in Louisville, Kentucky. The confirmed search and recovery force comprised at least 2 aircraft and 3 ships. A Pakistan Navy RAS-72 Sea Eagle maritime patrol aircraft, capable of wide area surface search using radar and low-level electro-optical and infrared sensors, The aircraft can also deploy sonar buoys and process acoustic signals, although it is not known whether specialist sonar buoys suitable for detecting flight recorder locator beacons were available or used. Pakistan Air Force Saab 2000 Airei, capable of wide area maritime surveillance. The Pakistan naval ship Zulfikar F-251 and the Pakistan naval ship Aslat F-254 and a Pakistan National Shipping Corporation merchant vessel. The fragmented wreckage and relatively contained recovery area are consistent with a high energy impact with the sea. Nothing visible in the currently published debris photographs establishes a widespread high-altitude breakup, although that possibility cannot be conclusively excluded without locating the main underwater wreckage. The water depth in the crash area is up to 3,060 meters, 10,040 feet. And it will obviously take some time and specialist equipment to locate the underwater wreckage and recover the FDR and CVR. So what are the established facts? The available evidence comprises the flight path, the ADS-B record, the cruise stability, the final descent, the crash location, and photographed floating wreckage. There are 875 ADS-B data points. There are 53 data points on the ground at Sharjah Airport and 822 data points in the air. The data are quite revealing, and we will analyze it in some detail. The ground and cruise data are generally stable and internally consistent, while the initial climb phase contains significant anomalies. Let's take a look at the weather en route. The available meteorological data show no adverse weather conditions capable of explaining a loss of control. Weather was therefore not an apparent contributing factor in the crash of K2 Airways Flight KTA 1732. The wind direction changed along the route, but the wind speeds were not severe and would have been routinely managed by the aircraft's navigation and flight control systems. There is also no evidence in these data of thunderstorms, heavy precipitation, strong turbulence, wind shear, or a microburst. At 16:17:27 UTC, the aircraft began turning right. Over the next 63 seconds, it turned through 50 degrees, departing from its previous flight path of 082 degrees true and reaching 132 degrees true. Altitude remains stable at approximately 35,000, plus or minus 175 feet, while speed remains stable at 441 knots, plus or minus 13 knots. The calculated turn radius was approximately 30 kilometers, corresponding to an equivalent coordinated turn bank angle of about 10 degrees. At 16:18:40 UTC, the event became much more severe. In 39 seconds, the aircraft continued turning right through a further 128 degrees while descending 5,350 feet. Its speed increased by 58 knots. The calculated turn radius reduced to approximately 7 kilometers. This corresponds to a nominal coordinated turn bank angle of approximately 38 degrees, although the aircraft's actual roll attitude cannot be determined from the ADS-B data alone. At 16:19:19 UTC, the aircraft temporarily reversed the turn. Over the following 38 seconds, it turned back to the left by 68 degrees, climbed 7,175 feet, and decelerated from 499 knots to 223 knots. This was a substantial reduction in ground speed, although the ADS-B data alone cannot determine the aircraft's indicated airspeed or its margin above stall. The calculated turn radius was approximately 6 kilometers, equivalent to a bank angle of about 18 degrees. Finally, from 16:19:57 UTC onwards, the aircraft entered the terminal phase. Over the next 122 seconds, it developed another right turn through approximately 173 degrees, almost completely reversing direction. During this interval, the aircraft descended 35,500 feet at an average rate of 17,484 feet per minute. The average horizontal velocity component was approximately 114 knots, and the average downward vertical component was approximately 173 knots. The resulting average slant velocity was then 207 knots at a calculated flight path angle of 57 degrees below the horizon. The final ADS-B data therefore show a progressive aircraft upset beginning at 16:17:27 UTC. The initial 50-degree deviation was a shallow and apparently controlled turn, during which altitude and speed remained stable. But from 16:18:40 UTC, the event became increasingly severe. The aircraft entered a much tighter right turn, descended 5,350 feet, and accelerated 58 knots. And between 16:19:19 UTC and 16:19:57 UTC, the aircraft temporarily reversed the turn and climbed 7,175 feet and decelerated considerably. This demonstrates that the aircraft was still capable of making a major change in trajectory. However, ADS-B data alone cannot determine whether this resulted from pilot input, automatic flight control commands, asymmetric forces, or natural dynamics of the upset. The climb was largely achieved through the conversion of kinetic energy into potential energy, and therefore does not establish that engine thrust was maintained. From 16:19:57 UTC, the aircraft was in its terminal descent. It reversed direction, descended 35,500 feet in 122 seconds, and developed an average descent rate of 17,484 feet per minute. Its final motion was dominated by vertical rather than horizontal velocity, and the calculated flight path angle of approximately 57 degrees below the horizon. Under these highly dynamic conditions, A bank angle derived from horizontal turn radius cannot be treated as the aircraft's actual roll attitude. The normal coordinated turn relationship assumes relatively stable speed, altitude, and attitude, conditions that clearly did not apply during the terminal descent. The data therefore show a temporary recovery followed by a catastrophic loss of control, from which no further recovery is evident in the available ADS-B record. The dataset demonstrates what the aircraft did, but does not establish why it happened. Determining the initiating failure, the aircraft's actual attitude, and the actions of the crew requires the flight data recorder, the cockpit voice recorder, wreckage examination, and the official investigation. The available ADS-B dataset does not indicate a persistent failure of the aircraft's inertial reference or air data systems after departure from Sharjah Airport. Apart from sporadic anomalies during the initial climb, the recorded position, altitude, speed, and track data remains stable and mutually consistent throughout the climb and cruise. The continuation of the flight with no publicly reported urgency or distress declaration, a mayday call or a pan-pan call, suggests that the crew did not initially regard the problem as requiring an immediate return to Sharjah Airport. However, the available ATC record is incomplete and cannot establish exactly what indications were present in the cockpit. The replacement of one of the aircraft's two inertial reference units is relevant to the investigation, but it does not by itself explain the accident. The second IRU had apparently operated normally on previous flights, and if it remains serviceable and properly selected, should have provided an independent source of attitude and navigational data. Investigators must therefore establish whether the replacement unit produced erroneous information, whether the serviceable unit remained available, how the cockpit sources were selected, and whether the maintenance work introduced any common mode fault. When the aircraft starts moving on the ground, the speed and direction are always accurate. The latitude and longitude align when tracked on Google Earth with the stand 82, the taxiways, and the runway. The Google Earth plots are particularly persuasive because the route is not merely smooth. It follows the actual paved surfaces in the airport, bends at the correct taxiway intersections, and aligns with the runway. Random positional error or three-decimal quantization could not reproduce that detail consistently. The takeoff roll starts at 15:02:04 UTC. The ADS-B dataset remains internally coherent during the takeoff roll and the early climb. At 15:03:28 UTC, at a reported altitude of 2,350 feet, the transmitted direction first ceases to agree with the aircraft's position-derived movement. The transmitted ground speed becomes erratic approximately 2 seconds later, while the altitude sequence remains credible. At 15:06:26 UTC, the altitude, speed, and direction data became largely stable again. They remained broadly coherent throughout the remainder of the climb and the initial cruise, although brief direction anomalies and a smaller number of speed anomalies continued. In the cruise at 35,000 feet from 15:48:41 UTC onwards, the altitude, speed, and direction data are valid and consistent. From approximately 16:19:27 UTC, the altitude, ground speed, and true track begin changing extremely rapidly as the aircraft enters a highly dynamic upset. Unlike the earlier climb anomaly, the position sequence and changing parameters continued to describe a coherent loss of control trajectory. The final timeline now shows that the ATC report did not mark the beginning of the anomaly. The aircraft's track had already begun departing from the airway roughly half a minute earlier, while the fully developed loss of control trajectory became evident about 90 seconds after the reported call. The Flight Radar 24 ADS-B dataset for K2 Airways Flight 1732 contains several independently behaving parameters. The altitude data are barometric and remain credible for most of the flight. Latitude and longitude are generally stable and geographically consistent, apart from the short disturbed period shortly after takeoff, while the aircraft was circling toward waypoint Ivuru. Ground speed data are stable for long periods, particularly in the cruise. Direction is the least reliable parameter, showing the greatest number of anomalies during the climb. Flight Radar 24 direction is true track. The magnetic declination in this case is 1.4 degrees, so it is not hugely significant. Despite these direction anomalies, the aircraft continued to navigate accurately through the published route waypoints. At about 16:18, the crew reported a navigation problem to ATC. The erratic ADS-B direction data cannot automatically be equated with a complete loss of the aircraft's navigation capability. The aircraft still reached waypoints Ivuru, Ladlo, Nadso, Damum, Aslom, and Alpor accurately. The reported navigation problem may therefore have involved a specific navigation source, a heading track reference, a comparator, a display or data distribution problem, rather than the total loss of positional navigation. For a Boeing 737-400 Classic, the standard architecture is generally not an integrated ADIRU in the modern 737NG sense. The Boeing 737-400 standard architecture uses two inertial reference units, left and right, forming a dual inertial reference system, together with two separate air data computers receiving pitot-static and temperature inputs. The exact installed configuration of APBOI should ultimately be confirmed from its aircraft records. The initial climb event was principally an intermittent inconsistency in the horizontal velocity data, while the final event developed into a real loss of flight path control involving the horizontal trajectory, the vertical trajectory, and speed. The current available evidence does not prove that the replacement IRU was the cause of the crash. Let's have a look at the data quality. The climb data are inconsistent. The cruise data are stable. The descent data are dynamic but coherent. ADS-B provides the aircraft's barometric altitude, the ground speed, geographical position, and true track over the ground. A large ADS-B dataset will normally contain occasional isolated outliers, particularly in areas of limited receiver coverage. An individual anomalous value does not necessarily indicate a problem with the aircraft. The more important question is whether successive data points describe a physically coherent flight path. During a normal climb, altitude and ground speed will generally increase, although neither will increase perfectly at every data point. During cruise, altitude should remain nearly constant, apart from step climbs, while ground speed may vary gradually with the wind speed and direction. During descent, altitude will decrease, while ground speed will normally reduce or change progressively according to the descent profile. The ADS-B record from KTA 1732 contains three distinctly different patterns. During the initial climb, the altitude data remains credible, but the transmitted ground speed and true track become intermittently erratic. At several points, the reported true track does not agree with the direction of movement calculated from the successive latitude and longitude positions. The transmitted ground speed also changes in a way that is not consistent with the position-derived movement. This is not simply a small number of isolated outliers. It is a sustained phase in which the horizontal motion parameters become inconsistent, while the altitude sequence remains coherent. The cruise phase is different. The aircraft maintains approximately flight level 350. The ground speed remains within a credible range, and the reported true track broadly agrees with the track independently calculated from the geographical positions. The data are stable, consistent, and largely constant. The final descent is also different from the climb anomaly. The altitude, ground speed, true track, and geographical position change rapidly, but they do so as part of a continuous and physically coherent trajectory. The data are highly dynamic, but they are not random or erratic. The distinction is important. Rapidly changing data during an aircraft upset are not necessarily unreliable. In the final phase, the changing parameters consistently describe a severe loss of flight path control. In the initial climb, by contrast, some transmitted horizontal motion parameters intermittently fail to agree with the aircraft's geographical movement. Other flights were examined for comparison. Previous flights by APBOI contain occasional individual outliers, as would be expected, but no comparable sustained phase of erratic ground speed and true track data was identified. Flights by other aircraft departing Sharjah also show stable and internally consistent ADS-B data during the climb. Other flights operating from Sharjah to Karachi show coherent data throughout the climb, cruise, and descent. The initial climb anomaly, therefore, does not appear to be a routine feature of the ADS-B coverage at Sharjah or along the route to Karachi. It appears to be a specific KTA 1732 issue. The public ADS-B record alone cannot determine where the inconsistency originated. It may have arisen from an aircraft-generated data source, the ADS-B transmission, the receiver reception, message timing, data aggregation, or Flight Radar 24 processing. The evidence establishes that the climb data contained a sustained inconsistency affecting ground speed and true track, while the altitude remained credible. It does not establish that the aircraft's complete navigation system failed, and it does not prove that the aircraft was subjected to deliberate jamming. The central finding is that the Flight Radar 24 dataset is internally credible over most of the flight. The cruise altitude is exceptionally stable, 35,013 feet, with a standard deviation of only 20 feet. And the independently calculated track agrees closely with the reported direction. The descent also shows close agreement between the transmitted and calculated parameters. This makes a persistent total failure of the position and motion data throughout the flight unlikely. It does not exclude an intermittent fault, an attitude reference problem not visible in the public ADS-B parameters, or a separate failure developing during the final minutes. The ADS-B data does not reveal the cause of the crash. It provides no proof, however, that the aircraft was deliberately jammed by Iran, and no evidence that it was struck by an Iranian missile. The recorded flight path did not enter Iranian airspace at any point in time. There are 12 possible reasons for a loss of control: unreliable attitude or heading information, autopilot or flight director malfunction, a flight control malfunction, stall or a high altitude upset, unreliable air data information, an electrical or common avionic bus failure, a structural failure, a cargo shift or a load control problem, engine or thrust asymmetry, severe weather or atmospheric disturbance, crew incapacitation or spatial disorientation, fire, smoke, or explosion. On the evidence presently available, the leading investigative categories include an avionics, electrical, or flight control malfunction, an aerodynamic upset, a structural failure, a cargo load control event, or a severe asymmetric thrust. These categories are not mutually exclusive, and one initiating fault may have produced several subsequent effects. Weather and a large external explosion are not supported by the evidence currently available, but neither can be formally excluded solely on the ADS-B data and the photographs of the floating debris. The initial deviation was recovered, suggesting that the first navigation anomaly was not itself the final loss of control event. K2 Airways owned and operated only one aircraft, the Boeing 737-400 freighter APBOI. The loss of flight KTA 1732, therefore, represented the loss of the entire operational fleet. K2 Airways Private Limited was formed in May 2018, but APBOI was the first aircraft delivered. The aircraft was registered in Pakistan and delivered to Karachi Airport on 6 July 2024. The Pakistan authorities have sealed the K2 Airways offices in Karachi. The aircraft was a Boeing 737-4M0 BDSF. BDSF means Bedeck Special Freighter, a passenger-to-freighter conversion associated with the Israel Aerospace Industries Bedeck Aviation Group. The conversion took place in May 2012. The aircraft is manufacturer's serial number 29210 and first flew from Renton on the 8th of January 1999. The registration changed from the USA N1786B to the Bermudan VP-BAR, and the aircraft was leased to Aeroflot as a passenger aircraft in April 1999. In July 2004, it entered service with Garuda Indonesia and registered as PK-BZ0. After the conversion to a freighter in 2012, it was registered as the Austrian OE-IAT and flown by TNT, ASL, and then FedEx. On the 19 April 2024, the aircraft was photographed in Malta with the K2 Airways livery, but with a Cayman Islands registration of VP-CFG. No evidence indicates that K2 Airways itself was registered in the Cayman Islands. K2 Airways describes itself as a private Pakistani airline based in Karachi and established under an airline charter license issued by the government of Pakistan. Since its registration, APBOI achieved an aircraft utilization of only 1.6%, defined as the recorded flight time as a percentage of the combined flight and stopover time. From its first flight under Pakistani registration until the accident, the recorded airborne time represented only 1.6% of the total elapsed calendar time. Its operational history included prolonged periods of inactivity, lasting respectively 166 days, 53 days, and 33 days, together with 29 scheduled departure records on 14 days that did not result in recorded flights. Those events indicate a poor operational completion and raise particular questions about dispatch reliability, although public flight records alone cannot establish whether each cancellation was caused by a technical, commercial, or operational issue. Some Boeing 737-400 configurations may be dispatched with one of the two inertial reference systems inoperative under restrictive approved MEL conditions. However, without K2 Airways MEL, we won't know the precise defect and requirements of intended operation. it cannot be assumed that the aircraft was legally or operationally dispatchable. The 9-day delay in Sharjah Airport may reflect the IRU defect alone, but it may also be due to the spare part availability, operational restrictions, additional defects, or uncertainty over the diagnosis. The statements from the crew's relatives are credible testimony that an IRU was reportedly replaced during the Sharjah stop, but they are not reliable evidence that a single defective IRU caused the 9-day grounding or that the IRU subsequently caused the accident. Reuters arguably gave the IRU angle additional prominence by obtaining an expert comment and comparing it with the Adam Air 574 accident. That made the story newsworthy, but it risks creating a causal narrative unsupported by the available evidence. The technical log, the defect history, the component removal tag, maintenance work package, and certificate of release to service would carry far greater evidential weight. Therefore, the reported IRU replacement may be relevant to the earlier navigation difficulty, but is not a satisfactory explanation of the final catastrophic loss of control. Treating the accident primarily as an IRU failure would be technically premature. A large number of items of floating debris have been recovered by the Pakistan Navy. The recovered wreckage includes a large exterior crown section carrying the K2 Airways livery and numerous flat interior cargo area panels. The cargo panels bear an alphanumeric installation grid, including 1M, 2M, 2A, 2B, 5A, 5B, 6A, 6B, and 10A. The smaller K2 Air marking appears on an interior cargo area panel, rather than representing a second exterior fuselage title. There are exterior markings on both the left and right sides of the fuselage, as well as smaller markings on the belly and the crown. The recovered wreckage includes both exterior fuselage sections carrying K2 Airways livery and interior cargo compartment panels carrying numbered and lettered position markings. What is our conclusion? The investigation is at its beginning and not at its conclusion. The evidence currently available supports careful analysis of the flight path and the recovered wreckage. It does not support claims that Iran jammed the aircraft or that the aircraft was shot down. Those claims may attract attention, but at present they remain speculation. The key to the investigation will be the location of the underwater wreckage and the recovery of the FDR and CVR. Any initial assessment must be subject to revision until further official data are released. Many thanks for watching. If you found this analysis useful, please subscribe to ensure you do not miss future independent aircraft investigations.